All right, to start off our Unit 11, we're going to talk about some general properties and help us get more familiar with what is an acid and a base, because that's what we're studying this unit. And this is just going to cover page 1, some super duper basic properties and definitions. So first, how do we know that something's an acid? Well, even way back before we could look at a chemical formula and say that formula tells us that things are an acid, there were certain general properties that we observed between things that we classified as acids. And the first is one of the easiest to identify, especially in consumable foods, is that acids taste sour. So if you think of some sour foods like lemons or even vinegar, it kind of makes you pucker. It tastes sour. You probably don't like drinking it much. It's not very sweet. It's only sour, but those are both acids. And they feel corrosive. Now, this word is a word we've talked about before, back when we talked about the NFPA diamonds. And when I say feel corrosive, I mean that acids do have the ability to eat through and dissolve flesh and other substances. So it's going to feel kind of ouchy and burning and stinging. That's the feelings you would feel if you did stick your hand into an acid. Now, acids react with bases. We learned about these acid-base reactions before. They form water and a salt. But acids also react with metals to form hydrogen gas. So these are some predictable reactions. If we see something having these types of reactions, even if we don't know what its formula is, we can tell that it is an acid. Acids also conduct electricity, and that's because they produce ions in solution. And we know that ions dissolved in solution are what we need to be an electrolyte. We learned that last unit. So all acids, because they produce these H+ ions in solution, do conduct electricity. Now, a quick little note about that H+ ion. Hydrogen ions tend to attach to water when they dissolve for stability's sake. They're not as stable on their own. So those H+ ions, when they react and kind of attach to that H2O, forms an H3O ion, like what I've shown you here, and we call that the hydronium ion. So later on this unit and kind of throughout this unit, you might see H+ ions referenced for acids, but if you ever see anything with this H3O+, that's just the acid in water, and all of these acids are in water, so we're all going to have those hydronium ions. So don't let that throw you off. H3O+, if you don't like the way it looks, if it confuses you, you can just cross it out. Think of it like an H+. There's no difference. That's just the way they actually exist versus kind of the simplified way that we see them detaching from those acids. Fourth property is that acids turn litmus paper red. There's a plant called the litmus plant. We can make paper out of it. And it can be all different colors to start with, but no matter what color it starts off, it will turn red, or a kind of pinkish red color, in the presence of an acid. And finally, we can measure the pH, and we're going to be calculating and measuring some pHs later this unit. All acids have a pH that is less than 7. Even starting at 6.9, that's slightly acidic, and the farther down we go on that pH scale, the closer to 0 we are, the more acidic something is. So those are some of our properties of acids. And like I said, we could see and classify things as acidic even before we saw their formulas. And so one of the very first people that tried to define acids and bases on a chemical level was Mr. Arrhenius. And this is what we call the traditional acid definition. Like we kind of saw up above in those properties, acids, he said, are substances that dissolve and break up to form H+ ions. So he said if they don't dissolve or if they don't form H+ ions, they're not an acid. So he thought that that would cover all of the bases and help us know and identify from a formula and a reaction what was an acid. Then along the way, we discovered that there were some things that had some of those properties up above, but that didn't necessarily form H+ ions in water. And so Mr. Bronsted and Mr. Lowry came along and they adjusted this definition. And this is going to seem very similar to you. At an honors level, this doesn't seem like a big difference, but this is a big important difference. Bronsted-Lowry defined an acid as a substance that donates protons in a chemical reaction. And protons are H pluses, because a hydrogen atom is already going to start off with just one proton and one electron, and that's a neutral hydrogen. So regular old hydrogen is one proton and one electron. Well, we have to lose that electron in order to become an H plus 1 ion. So an H plus 1 ion is literally just one proton floating around by themselves. So Bronsted-Lowry are basically saying that substances that donate H pluses, that give the H plus to another substance in a chemical reaction, is going to be the thing that is the acid. So it's very similar to the Arrhenius definition, where it forms H plus ions here. Making H pluses, or kind of giving H pluses, is a similar definition. In our base definitions, you're going to see one of the key differences between these acid-base definitions. But that's kind of the things that we look for in chemical reaction to tell us whether something is acting like an acid or not. Now, there's also two different types of acids, and we talked about the idea of a weak and strong electrolyte back in the last unit. Well, we have weak and strong acids as well, and it's kind of the same idea. Strong acids are the acids that produce H pluses, and these are the ones that break up completely. And all of the original acid, I have an example for you here, breaks up, goes one direction, and makes H pluses and NO3 minuses separate from each other. Those ions separate 100% of the time. All of this is turning into equal amounts of that and that. But a weak acid is an acid that does ionize, but doesn't stay ionized necessarily, or has very low ionization. Technically, chemists say less than 5% of an acid can ionize if we're going to call it weak. But the big idea, and you kind of notice it here, is this two-sided arrow, that sometimes this molecule of HF decides to break up and be separate ions, but sometimes these ions decide to come back together. This reaction is reversible. It does go back to being HF. So when we say less than 5% H pluses, we say that 95% or about of the time our acid is going to stay together as HF, and only about 5% of the time is it going to break up into being these H pluses and F minuses. So it spends more time like this, and if we have less H's, then that's a weaker acid. So that's our acid part of the page. We're going to go over the same details with bases now. So properties of bases. Bases taste bitter. Something like a banana peel, not the banana itself, but a lot of the peels and rinds, like an orange rind, the pith part of that tastes very, very bitter. And it doesn't really make you pucker your face just like a sour does. It's different, but it's still pretty unpleasant, especially for fairly concentrated bases. Bases also feel slippery. At a very strong concentration, you might still feel some burning. We actually call bases caustic instead of corrosive. They can still damage your skin and surfaces and whatnot, but they also, and even in those strong situations where it might be causing some damage, they're going to feel slipperier than water. So like I said, banana peels, one of the slipperiest substances. Cartoons use it all the time to show something super slippery that, a character is going to fall off on. Those are bases. Now, bases react with acids to form water and a salt. This is kind of just the opposite of what we said about acids. Acids and bases react together to make water and a salt, and we'll revisit that a little bit later this unit. And bases also conduct electricity, just like our acids do, except our bases produce OH minus ions when in solution instead of those H plus ions. They react with litmus paper still, they just turn it blue instead of red, and bases have a pH bigger than 7. Acids are less than 7, and bases are bigger than 7. I know I said greater than 7, but I keep in mind all of these B words when I think about my bases, that they are bitter, they turn litmus blue, and they have a pH bigger than 7. All of these B words go with that B of the bases. It helps me remember all of these properties. Now, we've observed those properties among bases, and then people came along and tried to define them. So as Arrhenius was defining acids, he was also trying to define bases. And just like with acids, he defined the base as a substance that dissociates in water to form OH ions, a lot like what we wrote up above, how they make these ions. That's what lets them conduct electricity. And so you would think that you would have to have OH in a chemical formula in order to have something be a base. But this is really where the big difference came along. Bronsted-Lowry came through and said, we have some things that act like bases. They're bitter, they turn litmus blue, but they don't have any OH ions in them. They don't have these OH groups that can come off and ionize to produce some OHs. So how can they be bases, but then they're not bases, according to this definition? So this is really where Bronsted-Lowry's change to defining acids and bases came in. They said that bases are a substance that accept our H pluses in a chemical reaction. And the OH part of that can help accept the H plus, but it didn't need to have an OH in it at all. As long as it had some way to accept a proton, to gain an H to that chemical formula in the chemical reaction, that made it a base. So this is completely different than that Arrhenius definition. It's all still focused on those protons, those H pluses, and just kind of what direction those H pluses are going. And we're going to revisit this Bronsted-Lowry definition in class and see how we can identify things as acids and bases just based on their definition. Now, just like our acids, we can have strong bases and weak bases, and the general idea is the same, that if we have a strong base, it is going to dissociate completely. It is completely breaking up. Notice my one direction arrow. All of this NaOH is going to be breaking up into its two separate pieces because NaOH is a strong base. But weak bases are something that ionizes very small amount, less than 5% on average. Notice my two-sided arrow. It's wishy-washy, just like our acids are. Sometimes our compound breaks up into these ions, but sometimes those ions, even after they break up, decide to come back together or stay as that compound and not ionize. So we have generally less than 5% of that compound ionizing to make those OHs. So, like I said, we'll revisit some of these definitions in a little bit more detail in the next couple of pages throughout this unit, but that's it for now. Hope it wasn't too bad.